Hello everybody, my name is Mahdi Asgari. I'm early stage researcher and Marie Curie fellow in TeraApps project who comes from Iran, lives in Pisa, and works as PhD student of Scuola Normale Superiore University as well as a research member of CNR Nanoscience Institute at Laboratory Unest. Today I want to simply talk about my research project which has received funding from European Union's Horizon 2020 Research and Innovation Program under Marie Skłodowska-Curie Research Agreement, which is mainly focused on development of room temperature Terahertz nanodetector. In order to do that, I'm gonna make you familiar with some basic concepts. First and foremost, what does Terahertz refer to? If we consider electromagnetic spectrum, there has been for a long time a gap between electronics and photonics application which roughly lies from 0.1 to 10 terahertz in frequency bandwidth, whose wavelengths correspond to 30 micrometer to 3 millimeter. But why is terahertz technology broadly considered in different research topics? To answer this question, I would like to mention that there are nowadays a lot of demands associated with terahertz technology in different scientific areas such as security imaging, medical science, especially medical imaging, information technology, characterization of material utilizing a specific technique named terahertz near-field microscopy, astronomical observations, pharmaceutical and drug diagnostic, and the last but not least, telecommunication and wireless technology. Now, I'm gonna briefly explain how the photodetection process can happen in field effect transistor. In my research project, I'm employing a field effect transistor which contains source, drain, and gate electrodes as well as an active area which is called the channel of FET. So this channel can be constructed based on either semiconductor iridium arsenide nanowire as one-dimensional material or semiconducting quantum dot as zero-dimensional material, or alternatively we can also consider new layered material, most importantly graphene, as gapless material, and black phosphorus which has intergoing properties due to different characteristics along zigzag and armature direction. Now let's suppose our detector is illuminated by terahertz incoming wave. What will happen? Since there is electromagnetic field associated with the light which can interact with the electrons in our channel, there would be an oscillation of plasma wave along the channel which yields to the photocurrent flowing through the source to drain, and then consequently it can be detected in locking amplifier as the readout. In this step, I'm gonna answer this question, that what would be the advantage of nanotechnology and nanofabrication for our application. As I mentioned before, once the terahertz impinge to our detector, it can be rectified, which is the conversion of AC component of incoming wave to the DC component detected by the locking amplifier as a readout. So this rectification of a terahertz can give rise to not only a strong nonlinearity of electrical characteristic of our device, but also can modulate simultaneously the charge density as well as drift velocity in our architecture. Consequently, by considering the plasma wave frequency in semiconductors, if we want to reach, for example, to 1 terahertz frequency, considering underlying formula which is inversely proportional to the length of the channel, we will see that for the different semiconductors, this length is given in order of nanometer as it's shown here. And now it's obviously proven that if we want to have effective and efficient terahertz detector, we should fabricate and construct our structure in nanoscale, and that's all. At the end, I would like to thank you for your attention and hope you like this video. Also, please don't forget to follow the videos of my colleagues in this project.